Okay. Shall we begin? Welcome to episode 2 of building a mechanical keyboard from scratch for the first time. We are currently halfway through a build of the mechanical split keyboard, and I have hit a bit of a roadblock right in terms of preparing for this stream. We had a little bit of a disaster with the right hand side of the keyboard, so I just want to quickly go over what the progress has been to date, and we're going to be looking at what we're going to do to fix our problem, because this is all part of the journey, right? We things don't always go smoothly. So let's quickly take a look at the first half of the keyboard, and here it is. Here is the first half of the keyboard now complete. As I say, this is a Redox keyboard, and if you check in the links in the description, you can see all of the parts, all of the project files are all linked. So if you go into the Thingiverse link, you'll find the model of keyboard that we're currently working on. So this is one half of the keyboard. I've 3D printed some keycaps because the intention is to design and 3D print a bunch of custom keycaps, backlit keycaps, two-shot. So they'll have like a clear section or translucent section for the letters and numbers, and then it'll have a opaque casting for the outside of the keycap. So right now, because I don't quite know what my layout is going to be, I've written on these keys with a Sharpie, and I'm going to pretty much play with different key mappings that I could potentially have and figure out what works well for me personally. And then once I know what that key mapping is going to be, I can make the keycaps custom. So this whole keyboard is going to be 100% custom. So the second part of the keyboard was going incredibly well, with this second half being hand wired. Right. Let's give you another view on that. Right. So that was working incredibly well, right up until the point I was trying to modify the base plate. So you'll notice on the left hand half of the keyboard that there is a button, and this button is quite important for programming the microcontroller. You need to be able to put the microcontroller into a programming mode, and it requires a double tap of this button. So I drilled this case incredibly carefully to insert this, because the hole for this button isn't in the 3D model. And this is where we come across our problem. I tried to drill the second half of the keyboard, and it didn't go so well, to the point where it delaminated and completely spliced this case. So we've got that to fix, right? And the way I'm going to fix it, there's two ways I could potentially fix it. I could bodge it and just like super glue this back together and continue drilling my hole. Or I could use this as a learning opportunity as to, you know, how can you use CAD programs to update a pre-existing STL file so that it takes into consideration any changes that we might want to make. So there's two changes that I want to make to this base. The first of which is putting the hole for the button to put it into programming mode. And the second is to actually have the enclosure to hold the microcontroller. I think the original project called for the microcontroller to be like double-sided taped to the underside of the plate, which I wasn't overly enamored with. Yeah, I think we're not going to do that. So I'm going to use this as a learning opportunity so that we can look to put a custom case together using the software that we've got available to us, right? I'm just going to quickly check the stream because my OBS at the moment is playing up a little bit. I just want to make sure we are live. And that everything is going well. Right, let's have a look. What do we got? Testing. My OBS at the moment is... The stream looks good, so I'm not going to mess with it. I'm just going to leave it well alone, and we're going to carry on just to make sure all is good, right? Let me see here. Oh, I tell you what I haven't done that I need to. See, everything's gone a little bit sideways because the failure happened with literally like 5 minutes to the stream going live. So things did go a little bit sideways. But that's real life. So what I can't see is live chat, so I'm just going to quickly fix that problem. So things did go a little bit sideways. But that's real life. So what I can't see is live chat, so I'm just going to quickly fix that problem. So things did go a little bit sideways. Oh, bit of duplication there. Okay, let's just quickly test chat. That's more like it. Okay. There we go. Perfect. Alrighty. So, where do we begin? We begin by opening up Fusion 360. And one of the first things that we're going to do is we're going to upload the STL file to Fusion. And I've already done that, but I'll show you exactly what I did. So ultimately what you do is you click the upload button, you select the file, and in this case it's the bottom right hand side that we've uploaded. We select upload, and then the file gets loaded here. So what I've now done is I've made this file editable. If I just double click that, we can see the STL file in Fusion 360. Now, the thing about this is that the file is pink, and that tells us that this is a mesh. And the problem with a mesh is that you can't edit it, right? So if I was to draw a sketch, let's undo that a second. If I was to draw a sketch on, let's say, this surface here, in fact, it's not allowing me even to select that surface. So let's try this instead. Okay, so we'll select this surface here. If I was to put a circle, right, let's say I wanted a hole through the bottom of this, and I click my circle, do the extrude as you normally would, and drag it here, we're not actually interacting with this mesh. So this object exists. We're not doing a Boolean operation. We're not cutting the object. We're not changing the geometry of the STL file. So one of the problems that you get when you import an STL file is, one, it's a mesh, and two is that you've got all of these triangles. So STL files are all built out of triangles, and that can be a little bit problematic when you are doing your model, right, or updating a model. So what we're going to work on is, first and foremost, converting this into a mesh that we can modify, and then we're gonna make some changes to this. All right, so first and foremost, let's go to the home view, and we can see the coordinate system of the model means that it's on its end. So we want to rotate the model so it's in the plane that we want it. So let's do that. Let me see here. M for modify. We're going to rotate the body. I'm going to select roughly the origin. And then I'm going to go to the side view, and I'm going to rotate the model over until it's flat, like so. All right, so that's the first thing we're going to do. I'm going to turn on the global origins so I can see where this is in relation to that. And you can see it's slightly offset. So I'm going to again move. And let's see here. Let's go move point to point. So we'll choose the center of that object, and we're going to move it to the origin of the overall design. Okay, so now we've got our model where we want it in space. What we're going to do is we're going to convert it into something which we can edit, an editable body. And to do that, we have to go to the mesh menu. And once in the mesh menu, we need to go to modify. And out of all of these options here, we need to convert mesh. So we select the mesh body, and then we click on OK. It's as simple as that, right? Now, depending on how complicated your model is, will depend on how quickly it will convert it into an editable model. Some really high polygon count files can really cause problems with Fusion, and it may actually throw up a little bit of an error. So let's now do the change, or the first change that we want. The first change is that we want a hole just around about by here to allow us to insert our button to put the microcontroller into programming mode. So you'll notice as I'm moving my mouse around here, you'll notice that we're selecting all of these individual lines and faces, edges and faces that make up the triangles. So that's a little bit awkward, especially when you want to try and sketch. So to get a clean surface for us to sketch on, we're going to go back to the solid menu, and we're going to use a construction plane, and we're going to select one of the faces, one of the many faces of this model that we're going to put a construction plane on. And you'll see that construction plane in yellow. Let me turn the global origins off. And we're not going to move it in any of the sort of XYZ coordinates. We're going to leave it on that face. But now you'll notice we can select the edges of this construction plane. And we're going to just stretch it up and stretch it down so that we've got something we can click on. So now we're going to put a sketch on this construction plane. So let's do that. So we'll click the Create Sketch button and then click the construction plane that we put in place. So now we've got a clean canvas that won't pick up any of the artifacts that the model actually has in the case of this. It's an STL file, or its origin is an STL file. So now we want our placement. So I'm going to project the upper edges of this body and the lower edge here. And now I'm going to put a line in between those two, and there's a reason for that. If I turn the body off, the lines that we projected have actually turned like a pink color, and that's how you know that they are projected. All right, so let's bring that body back, and now I'm going to put a construction plane in the center of this face here. And I need to be mindful of the fact that we've got a chamfered edge and we've got an internal floor. Ooh, that's actually a really good point. I think it's a really good catch. So let me just undo these operations that I did. I'm going to change the faces, or the edges that I'm going to project. So what I'm going to do is I'm going to project this line here, this line here, and now I'm going to come around and I'm going to project this triangle here, which tells me where the floor of the internal model is, like that. And now I can put a construction line between these points. And now I can go from the center of that. Now I know it's the center because as my cursor goes up this line, you'll see a triangle. And that tells me that that is the center line of that upright, that vertical. All right, so now I need to know the diameter of my button. So let's get one of the buttons out and we will measure it with a set of digital calipers. So yeah, this was something that I wasn't intending doing tonight, but things don't always run smoothly, and sometimes you have to course correct. So that's what we're doing. Minor course correction. But in the end, it'll mean that we'll have a 3D printable model that will work straight out of the gates next time. All right. All right, let's get the digital calipers and we can work out the diameter that we require. So let's have a look here. Okay, it's a 6.6 millimeter diameter, so we're going to give ourselves a couple of millimeters grace. So we're going to uplift that to a 7 millimeter hole. So let's place that on here. Let's get out of our construction mode and select. Let's get rid of the body for a second. Okay, and we're going to go 7. Oh my word. Wow. Look at that. So I don't know if you've noticed this, but this model is huge. Why is this model so big? So if I inspect the top here with the bottom, that's 132 millimeters. I don't think that's right somehow. So something's happened when importing the STL file, causing it to be somewhat larger than it should be. And I think that's got a scaling factor of about 10. Yeah, it looks like it's got a scaling factor of 10. So that is crazy, right? So we've got this file is so much larger than it should be. All right, so let's quickly undo the sketching and let's bring us back to the original model. So I'm going to scale this model. So we're going to modify it. Let's have a look. Where are we? Going to go scale. Okay, so if we think it's a factor of 10, I think that's 0.1. Okay. So now we need to confirm that that is correct. So what's the easiest way of doing that? That edge, the bottom edge, 13 millimeters. That's better. That's much healthier. All right. So let's move the body. I'm glad I spotted that, right? Okay, that's one origin point. Now the target needs to be selected. There we go. Okay. So that's been somewhat problematic to start with. So let's go ahead and redo the things that we've just been talking about. Like so. All right. So we'll put a sketch on construction plane. We're going to project these upper vertices, these upper edges, and we're going to project this lower edge here. I'm just going to speed run this a little bit because we're running behind time. And there we go. Let's get rid of the body because it's a little bit confusing to see, and let's get a straight on edge. And now let's put our 7 millimeter hole. That is much better. Okay. So let's bring the body back so we can see, and let's dimension from this edge here to the center. And we'll make it 15 millimeters. Make it 20 millimeters. Okay. So now, when we do the extrude of this circle, we can punch through the side of the model. Like so, and we've now got our hole for our button to go in, which is exactly what we need. Perfect. Okay, so the is bring in my mount for the microcontroller and get that modeled so it's part of the case itself. So let's go ahead and bring that in. And let's look at my project file. Now I needed to modify this a little bit. Let me just quickly modify the sketch. Maybe this sketch here. Okay, and what this will enable me to do is I can essentially bring this part in. Let me just hide that top piece. Okay, so I can bring this in and I can merge it into the design. In fact, I think that's going to take us too long. So what I'm going to do, I'm going to go straight away and I'm going to save this file. We're going to output it, and then we can get back onto the keyboard while this is printing. So, because I know my microcontroller case works. I'm going to save this as a mesh. I'm going to save this as base. Right. Dash mod. Okay, let's stick it in the downloads folder. And now we can bring our Prusa slicer up. We can load the file. All right, and there it is. Do a quick slice. Perfect. It says it's going to take 2.5 hours to print. So by the end of the stream, we may have a case. Right, that's uploaded to the printer and is on its way. So now we can get back to wiring the keyboard. Okay. So let's go ahead and get sorted out for that. So we'll bring in our stand. Mount the keyboard. So all the diodes are done, and while I was wiring up the keyboard, the other keyboard half, I came to the conclusion I had a better way of wiring the the columns even. So what I'm going to do is a very similar thing to what I did last time, which was to wire the column. But okay, so I wired the column this way from top to the bottom. Now, what that actually caused was my wires needed to be routed back to the top and across. So instead of doing that, I snipped the wire off, and I soldered the wire from the top and brought it over. So that's what we're going to focus on right now. So we're going to bring in the enameled wire. And let's grab our solder. Let's get the iron back up to temperature because it's gone to sleep. I will grab my magnifiers. Don't you just love it when things go sideways at the 11th hour? It's like, it really tests your ability to think on your feet. But I absolutely think that this is... I may even reprint the other case just to get the de facto hole. Hey, silent mode. How you doing? Hope you're having a good evening. So yeah, we just had to... I don't know how long you've been hanging out in chat, but just had to fix a problem which I could have well done without. So the base of the right hand keyboard part actually split as I drilled a hole for the push button that puts us into the programming. Okay, so you just got here. So yeah, I just had to edit the STL file because, as I say, I was drilling a hole for the button, which I did successfully on this one. And this button is used to put the microcontroller into its programming mode. And yeah, it literally just destroyed the model. So thank you. Thank you, universe. So I'm in the process of printing out the next base. It says it's going to take approximately 2.5 hours. I don't actually know how long it's going to take, but yeah, it is a little bit of an ouchie, but you know, it's a learning opportunity. So I just spent some time on stream talking about how to modify an STL file. So if that is something which you are interested in doing, modifying an STL file with Fusion 360, I've just walked through that process, and probably will make a little video out of that, maybe. I think that would be quite a useful thing to have on the channel. Okay, so what we're going to do is I'm going to, like before, I'm going to anchor the first wire. So this is the bottom of the keyboard, this is the top of the keyboard, and I'm going to route everything up to the top on each of the columns, because my microcontroller is going to be just here, so my cables naturally want to be here. I do have to do some routing with my rows, but the columns, they can naturally terminate at the top row, and the cables will come feed along here and not have much of an issue getting to the microcontroller. So let's... Yeah, it's why you tend to design stuff yourself, right? Sure. Well, I mean, you've got to remember, this is a squirrel-hole project, right? This is a project that I never intended on doing in the first place. And I just have to get this out of my system, and then I can focus on the projects that I have on the bench. That's definitely in the order here, right? So okay, so what I'm doing here is I'm looping this enameled wire around the post of the bottom switch, and then what I'm going to do is I'm going to come in with some solder, and I'm going to tether that wire there. Wonderful. I'm going to give myself a little bit of slack on this enameled wire. And then I'm just going to route the wire all the way down. And we've got, what is this? This is, what's the size of it? It's 0.063 millimeters. I don't know what that is in AWG. The American wire gauge. I don't know what the specification of the wire is. Let's see if we can use some tweezers here to speed this up a little bit. This process is all about finding hacks, and we found some hacks with doing the diodes. We need to find some hacks with this like enameled wire. So we've got a very incredibly fine piece of copper wire which is enamel coated. So it means it's not conductive up until the point we decide to solder it. Once we solder it, that enamel burns away and it is conductive. And we can get away with having such fine wires because the wire itself isn't carrying a large amount of current. It's a signal wire. So we can get away with it being so fine. Now, if this is carrying like current, that would probably be not a great idea to have a wire this thin, because effectively this wire would become a fuse and burn itself out. Okay, so that should be us. I'm going to snip the wire here. I'm snipping the wire because from an assembly perspective, it's a little bit easier not to have the tails of the wires dangling around. I did when I did this on the first stream, it was a little bit of a challenge. Yes, I have wrapped the wire around the pins. I'll show you on the next row. I'll do a close-up on what I'm doing here. I'm just now coming through. Now I've anchored each end. I'm coming through and just making sure that the enamel wire is soldered. Now we need to make sure it's not only like bound up in the solder, we actually need to make sure that it is making an electrical connection. So we're going to use the multimeter to beep test each of the pins to make sure that the column is intact. So we're in continuity mode, the mode that beeps. I don't know whether or not you're hearing the beeps, but let's go from one end to the other. Yes, 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 yes. So we have full continuity in here. So if I go from this pin to this wire and we make them touch, because this is enameled wire, it's insulated. Okay, so that's the first column complete, and we'll move on to the next one. So let's bring you in a little bit closer so you can see exactly what we're doing here. I'm trying not to pull the camera over. I'm doing a very poor job, right? Boop. Let's go to the camera settings. Okay, I'll give you a close-up. So what I'm doing is on this first pin here, what we do is we wrap the enameled wire around the pin. And we do a couple of turns. I mean, I could probably make it a little bit easier on myself by having a bit of extra wire. I might also be able to make it easier on myself. There we go. A little bit more wire and a little bit more. And he says he makes it easy for himself, and then he pulls the wire off. Right. And it's very difficult for me to... I'm hoping you're getting a good view of this, considering my hands are pretty much in this. So I'm hoping you can see, or at least get the gist of what I'm doing. Right, so there we go. So that's now wrapped about 2 or 3 times around that first pin. Okay, so we're going to come in with the soldering iron, hit it with a bit of heat to warm it up, bring the solder in, and we make sure that that is bonded to the pin, and that serves as an anchor point. So next, what we're going to do is we're going to come down the column, or should I say come up the column, because remember, this is the bottom, this is the top. The keyboard is currently upside down, it's inverted. And we're going to wrap the enameled wire around each of the pins at least once on the way down, on the way up to the top of the keyboard. We can nudge. We can nudge these down the pin if necessary. And then we get to the last one at the very top of the keyboard. Okay. Done that final wrap. And we come in with the soldering iron. And we just solder this pin. Trying not to touch the 3D print with your soldering iron, Steve. Come on, mate. Here's me trying to get a good angle. I'm not paying attention to where my iron is, and I kind of touched the plastic there. That's cosmetic, so I'm not overly worried about that, but I don't want to do that too many times, otherwise I get plastic on my iron. Okay, so now that is complete. We can come back through here, and we finish the soldering job on the remaining pins. Okay, and now beep test, just to make sure that everything is in order. So let's do that, shall we? Beep beep, continuity mode, the mode that beeps. That's connected, that's connected, that's connected, that's connected. Okay, so column 2 is complete. So we're now going to go through to the next column, and we're going to go through these one by one till we get to the end. Did that make sense? Silent mode? Hopefully you had a decent view of that and that made sense. So it's really hard. Maybe if I unplug that, you're going to lose the camera because it's on. Dang it. It's trying to get you guys in a good position to see what I'm doing. That is something that I need to spend some time in sorting out. I would have, like I say, I would have had a little bit more setup time to get this just so before the stream, had it not been for the fact that I had that catastrophic failure of the case. That really wasn't cricket. Cool. Glad it made sense. Okay. So the objective of the stream tonight was to get this keyboard completely wired and get the firmware installed on it. Now, it wasn't necessary to get it operational, because I'm very aware that I have to make sure that I've wired the interconnect between the two keyboards correctly. That the firmware understands how to talk to each half. So we got the same firmware on both halves, and through some programming wizardry, the device figures out which half of the keyboard is which, and means that the QWERTY part of the keyboard is on the left, and the other keys, like IOP and all that sort of stuff, are on the right-hand side of the keyboard. So, yeah, I've got a. There's a couple of things that I'm aware of that you know, we may get to work first time, but the chances of that are slim. I would say the chances of us having a problem that we need to try and debug is reasonably high, considering that I've never done this before, and I am blindly following somebody else's instructions. That's going to cause us a bit of a challenge, right? Potentially. So we'll see how things go. I'll take the win if it works first time, but I'm not expecting it, right? That's I like to think of it as like healthy pessimism. because, you know, following instructions from some stranger on the internet is always the way to go, right? What could possibly go wrong? I mean, in all fairness, this is relatively straightforward. I mean, you can tell when you're violating power problems if you put like a 5-volt to ground and create a dead short. You know, if you've been around electronics long enough, you can spot those things. So I've got no issues with the thoughts of releasing the magic smoke. If there is a short in the system, that will be because of my workmanship as opposed to the design of the keyboard. Okay, that's the next column wired. Famous last words, right? Famous last words. Failure is always an option. You know that whole Mythbusters mantra, failure is always an option. Gotta love it, right? So here we go. We're buzzing out column number 3. We're in continuity mode, the mode that beeps. Yes, we have continuity there. Yes, yes, yes. So column 3 is intact. It is in good shape. I just want to prune this wire a little bit, because it doesn't need to be, I don't need to have a little strand of hair sticking out the side of my project. So let's get rid of you, and let's get rid of you, because I don't like you there. That feels like a problem waiting to happen. Did I get it? No, I just made it go into a direction that visually looked like it was gone, but it was still there. Right, okay, now that's gone. Next column. Next column. Right, so anyone in chat, if you have any questions about what I'm doing, feel free to ask away. This is an interactive session, and you are more than welcome. I will do my best to explain what I am doing to the best of my ability. And yeah, this is all about trying to get the squirrel moment out of my current sort of immediate future. Squirrel hole moments are an absolute bane. They're a momentary distraction that take, like 2 weeks later, you realize you're down a hole that you never intended going on. It's like, really? Really? Why did you do this to me? Okay, I see we've got a question in chat. I will pick that up once I've anchored this point here. Perfect. Okay, so question. Caleb, let's have a look at what we got going on. Okay, so the question is there an issue of the wire conducting across the resistor posts, or are they not touching? Right, so let me get you a good view of what we got going on here. So we have a series of cherry MX blue keys, and we have what we're assembling here is a matrix of rows and columns. The rows are made up of these diodes, and diodes only allow electricity to flow in one direction. And the reason that they are there is so that when I press this key here, I don't have the electricity feed into this row and work its way up to a different route back to the microcontroller, causing ghost key presses. So these diode wires are conductive, right? They're bare metal. I am using this enameled magnet wire for the columns. Essentially, this is a very thin copper wire which has an enamel coating on it, making it electrically insulated. It's pretty much an insulated wire, right? So even though they visually look like they are touching, and they physically are touching, they do not conduct electricity. So when I wrap them around the posts of the switches, the enamel burns off when I solder the wire to the leg of the switch itself. So it's a really efficient way of building the circuit. I don't have to strip wires, which trying to strip these types of wires and do that reliably and make it look nice, it's horrible. So I thought I would experiment with some enamel wire. This enamel wire is actually destined for another project. I am in the process of building a Fender style jazz bass for my youngest son, and this is the wire that will be used for making the pickups. So, as I say, see, that was less than desirable. So this wire is just snapped. It's incredibly thin. So what we'll do, I could just like solder on, right? But I'm not going to. I'm gonna replace that short stretch. But Caleb, does that make sense? Hopefully that answers your question. There we go. That's the wire off, and we'll start that column again. Had that been a little bit, longer, I might have like carried on. But seeing as it was so short, you may as well just restart the wiring of the column. Okay, cool. Ready. Let's keep moving because we've got the columns to complete, and then we've got to prep for the comms between microcontrollers. As I mentioned earlier, there are two Arduino Pro microcontrollers in this project, and they communicate between each other using the I2C communications bus, which effectively is a two-wire system. You have a serial clock and serial data. You do have to have plus 5? I think it's plus 5 volts. Yes, we're using plus 5 volts because we are using the TRS cable to power the other device. So yeah, we're taking ground and we're taking 5 volts across to the second controller. But ultimately, all you need for I2C communications is 2 wires, which is really handy for this project. Oh, you're very welcome. You are very welcome. So the Fender Jazz Bass project, we are awaiting the arrival. I say arrival. We are awaiting me building a CNC machine. We're scratch building a CNC machine because I can't afford the machine size that I need to build the neck. So it's we do a lot of things from scratch on this channel, which means we can jump around projects. And I would like to see if I can get a little bit of traction. I would ultimately love to get a channel sponsor that would say, "Hey, Steve, here's a large CNC machine that you can use." That would be awesome. But I'm not waiting for that to happen. I'm just taking the bull by the horns and I'm building my own CNC from scratch. So, and that is, I need a CNC machine large enough to process the guitar neck in one side of the guitar neck in one operation. So we will be getting back to the jazz bass. I'm making a pickup winder. So yeah. PCB waste sponsor coming soon. That would be nice. That would be nice. That is one of my goals for 2025, is to get a channel sponsor. If I can get more than one, that would be awesome. And having a channel sponsor would mean I would be able to get through projects a little bit quicker than I am currently working. But I'm going to be focusing on a couple of different metrics. I've got some Fusion 360 tutorials in mind. There we go, last post. And I bet you guys have got an absolutely rubbish view of that. My rather large sausage hands. Oh, awesome, awesome. So what made you choose a Dactyl keyboard? So I've got a chassis for a Dactyl, which I printed out. Where did I put it? Did I put it back in the trash? I might have done. Yes, I did. So yeah, I've got a Dactyl. Chassis that I was looking at hand wiring, and the problem I found with the Dactyl, or this particular chassis, was twofold. The spacing between the buttons was too great, and I was finding that stretching to the keys was an unnatural movement. One of the reasons I'm building this keyboard is for ergonomics. And that unnatural movement told me immediately that prolonged usage of this particular chassis would cause me repetitive strain. So that already discounted this particular chassis. There are ones with a smaller spacing on the keys. I could have gone down this route, but I chose not to for the second reason. If I turn this sideways, you can see the curvature of this Dactyl keyboard, and you'll notice that they're in kind of like pairs. The columns are in pairs. This one's kind of like split, but technically they're in pairs, and this promotes touch typing, right? Because your fingers naturally go to these places on the keyboard. And unfortunately, I am not a touch typist right now. I'm kind of an intermediate. So I felt that the Redox keyboard, being a flat plane, would be a happy medium between a full touch typing experience of the Dactyl versus, you know, a standard keyboard. So I thought it was a healthy middle ground that wouldn't turn me off completely. So yeah, I was thinking of a Dactyl, but yeah, that whole sort of touch typing thing for me was a bit of a showstopper. So Caleb, have you wired a keyboard before, or is it your first time doing it? Or are you kind of like a veteran of hand wiring keyboards? And if you're the latter, how am I doing? Because this is my first go at it. Okay, let's test the column. That print is printing nicely. Continuity mode, the mode that beeps. So I like to test as I go. Okay, we got continuity along the full column. I like to test as I go, simply because if there are any errors, I can deal with them there and then, as opposed to a long, drawn-out debug process later on. But yeah, silent mode. I absolutely would love like a PCB way sponsorship. I'd like any type of sponsorship, to be honest with you. But I guess it's going to be interesting in the coming month how the whole tariff situation plays out in the United States. The vast majority of my viewers on the channel are US based. And a PCBWay sponsor, because PCBWay is based in China, that may not be the smartest move, right? Because my American viewers may not be able to take advantage of their services, per se. But you wanted to experiment with the bend in the frame. It'd be lighter linear switches, the touch typing work. Well, listen, I'm a great believer in that, you know, what's right for me may not be right for you. It's a unique situation, and if it, you know, the proof is in the results. The method might be different, but if your results are successful, then nobody can argue. But yeah, I'm having a little bit of a squirrel hole moment. So this is a mental itch that I'm having to address. Now, ideally, I should have a fume extractor. I know we discussed this on the previous stream. This is leaded solder. I wouldn't recommend doing what I'm doing if you solder a lot. You probably want to invest in a fume extractor, right? But I don't solder a huge amount, and I've got a technique. Oh, thank you. I'll give you a bit of a close-up on that. I'm trying to make this as clean as possible. One, because everybody's watching, right? Everyone's watching, and and secondly, it makes it easier on the you know, when I'm doing the wiring. It makes it a little bit. You put it, yeah, full fat solder, right? Makes it a little bit easier on like diagnosis. So the temptation is to run ahead and just kind of like spaghetti junction it, but that only causes problems further down the line. So I'm trying to practice my patience. I mean, I already shouldn't be doing this project in the first place, right? This I should be working on other things. I got other stuff I should really be doing. But yeah, surface mount soldering is an art into itself, right? So I've got a little bit of surface mount. I've got a little bit of surface mount under my belt with this little bad boy that I designed and made. And for that project, we did a... I'm not sure if you're familiar with the Lumen PMP, but it's a pick and place machine for placing surface mount components. Well, I did a source build of the Lumen PMP. I resurrected my first ever 3D printer, Frank. I resurrected him into the pick and place machine, which is sat just behind me. So it's the Franken PMP. I named my 3D printer Frank because he was Frankenstein together from all sorts of like bits and pieces, left, right, and center, and taught me everything that I needed to know about computer numeric controlled machines, CNC machines, which 3D printers are a variant of, and has allowed me to go on to bigger and better things, such as restoring a CNC machine, restoring an industrial grade laser cutter, yeah, so I'm very grateful to Frank. Frank's taught me a lot. Okay. A quick 3D print and a spare PC fan. Yes, this is true, but you also need a power supply. For said 3D, for said fan, right? So, okay, so that's my rows and columns now complete. So let me just do a quick view of that. So that is the rows and columns all set up nice and neat. So, but Frank is over here. So this is the Lumen PMP built from scratch. I built a reflow oven, and I was able to like batch solder my boards like this. So it's a little bit guerrilla setup, but it works, which is what matters, right? The fact that it works is the important thing to me. Okay, up next, I guess we need to start working on the 3D print's going to be a while from what I can see. It's supposed to be like 2.5 hours, but it could be lying. Because print times, you know, they never lie, do they? They always run to the amount of time they say they're going to. So what I'm going to do is I'm going to use the old base. And then we're going to prep the column, prep the rows. We need a microcontroller. That's a good point. Where's my microcontrollers? So I need some additional components here. So I'm currently sifting through my box of bits. My project box. There you go. We've got a microcontroller. We've got a TRRS socket. I think that's everything we need for the moment. Gary, welcome in. Might as well be MySpace. So Gary, talking like that, you must have come in from somewhere else, probably from Twitch. Now I got to learn who people are, right? I got to learn who people are from the Twitch experience. Okay, so let's get you a decent view of what I'm about to do, because we're gonna get a little bit brutal here. 101. You're gonna have to send a message in Discord, right? Because otherwise, I'm not gonna know. Right. So I've left the legs of the diodes long. So what we're gonna do now is just trim them, so that they're inside the case, so they don't catch this edge here, right? So let's go ahead and just trim these off to a nice length, accessible for wiring. Now, I'm not going to insulate these diode wires when I solder these up. They're that far apart and there's nothing moving inside here, so there should be no reason that I need to insulate them with some heat shrink or anything like that. I will insulate the TRS socket because we've got 5 volts and ground and all that sort of stuff, and we definitely don't want a short, right? So that's definitely something we're going to do. So this button hasn't traveled well. Well, it's just come apart in my hand. Oh, well, that's just amaze balls. Okay, can I lock that back in? It's almost like it's a press fit and it's popped out of its housing. Okay, I'm not going to mess with that. I'm going to mess with that. We'll sort that out after. That's a future Steve problem. Right, okay, so we need 1, 2, 3, 4, 5. We need 5 pieces of wire that we're going to use to route up to our microcontroller for the rows. So all we're going to do is literally just batch through these now. Just stripping the ends. Okay, let's get a bin to put the trash in. There we go. Let's do these. See if I can do 2 in 1. I used to be able to do like a batch of about 10, but I don't have decent. These are flush cutters. They're not wire cutters. I used to be able to strip like 10 cores in one go. Perfect. Happy days. All right, so that's those stripped. And what we're going to do is we're going to just give these wires a little twist. Give you an overhead view because this angled view is probably not the most appropriate one just for a minute. So we're going to give these wires a bit of a twist, just to make sure we don't have any straggly strands. Okay, just work through each one, and then we're going to tin the wire, and then we're going to sweat them onto each of the rows, and that'll be all of the rows prepared. And then we'll finish up by actually getting those connected to the microcontroller. In the replay, we are building a Redox keyboard. If you check the links in the description, you will find links to the Thingiverse files that we are using, and those files include the 3D prints, but also the wiring diagrams for hand wiring these halves of the keyboards. And we're on a second half. The first half is complete, and I flashed the firmware onto it, and I can confirm that it is operational. It works. So the challenge that we're going to have is getting the second half working, because there's some complexity in the second half, in that first and foremost, how does these two microcontrollers know which is the left half and which is the right half? That's the first thing. And secondly, is that the USB, I mean, which side of the USB were we going to plug in? My preference is to have the right side of the USB plugged in, the right side of the keyboard. So will that work? I have no idea. I have no idea. At this point, this is, you know, this second half of the keyboard is going to be like pure experimentation, right? So we've got a bit of work to do, and it could go south, right? So now I'm just going to sweat a little bit of solder on the tips of each of these diode legs. I don't want the diode leg to heat up too much because I don't want to burn the enamel, because then I will get a short. And that won't be good. Yeah, right. So eventually this keyboard will be backlit. Eventually this keyboard will be backlit. Well, I'm going to be building, or I'm going to be making some custom two-shot keycaps. I've already made, that didn't hold. I've already made a set of keycaps custom to this project already, and they're a little bit of a proving ground. There is some problems with my keycaps, specifically. So there are three types of keycaps that we're using. There's a 1U, 1.25U, and a 1.5U. So my 1U keycaps are absolutely fine. The 1.5 and the 1.25, they're too tall. So I think what I'm going to do is, I found a parametric model for keycaps, which when I modify it, the proportions are out. So I think what I'm going to do is I will model my own parametric file for the keycaps. Okay, so that is now our rows complete. Let's just take a look at the 3D print of, the reprint of the case. That is currently still on the bottom level. It's not just on the sidewall. So once it gets to the sidewall, it will start to pick up the pace a little bit. But right now, we're waiting on said print. So I've not got a color code convention. It's just a random set of colors. I don't really care at this point. So that's fine. Right. What else can we do here? Let me put this switch to one side because I will lose it. It needs to be repaired. We can do that after. Right. We realistically are now at the point where we should be soldering up the microcontroller. Right. So if I bring in the base. Okay, so this is the bottom. This is now the top. These wires are going to make it up to the microcontroller, which sits here. Let's see if we can see it better a little bit. So yeah, the microcontroller is going to sit here, and the wires are going to be trained up and across, trained up and across, trained up and across. So do I think I could build this for $100? So in terms of components, yes. If you're asking me, can I make you one for $100? No. but yeah, I mean, you can probably pick up a set of Gatron keys. So these are recycled Cherry MX keys. You can pick a set of Gatrons for probably about 30, 40 bucks. The In fact, if you check the links in the description, there are Amazon affiliate links to all of the components that I've used here, right? I've swapped out the Cherry MX for Gatrons, but you need 2 Arduino Pro Micros. You need 70 key switches at least. You need a reel of filament. You don't need a full reel. Oh no, well, Gary, so filament's about $20. The switches were about $40, so that's $60. Then you've got the diodes. So let's call that $5 for the diodes, for 65. You've got the TRS connections. Let's call it another $5 to $70. And then you got your keycaps. So I mean, you're probably going to be hitting that. You're going to be hitting that close to that $100 mark, I would say, if you went out and out buying those components. If you made the keycaps, you could probably make them, you know, a lot cheaper than purchasing them. But it all depends upon your source, right? Right, and I mean, so behind me, I'm going to be building, well, I've got a mostly built pickup winder for the jazz bass. And I think in components, that's cost me about $5. And it automatically counts the number of turns. So, I mean, being brutally honest, it wouldn't make much sense to me to buy a pickup winder for like $350 when I can make it for $5. Okay, it's not the greatest thing on the planet. It's quite noisy, but right, it's a squirrel-hole. Thank you for joining. Thank you for joining me on this squirrel-hole adventure. Right, this wasn't supposed to be the project I'm working on. Right? So I call this a squirrel hole moment in the sense that it's a momentary distraction that 2 weeks later you realize you're 3/4 of the way through a project you never intended starting. so yes, right? I got to get it out of my system. But thank you for joining me on this journey. Right, so let me show you. I don't know if you saw the keycaps that I've made. Right, so these are the keycaps that I've made. These are resin printed, and I don't know my key layout. So letters and numbers I typically know. So I've written on my keycaps with a Sharpie, but I'm going to be doing a video on making 2-shot illuminated keycaps using resin printers. Using resin printers, silicone molding. Yeah, this squirrel moment project. Yeah, this squirrel hole project it's taking on a life of its own. So yeah, I never intended this. But it is what it is. And the question is what do we learn in the process? Right, okay, let's bring up, I got to remind myself, right? So this is the right-hand side of the keyboard. You're spelunking? Right? This is like, we're off the beaten track. Roads, where we're going, we don't need roads. So let's have a look. Right, so we're working on the right hand side of the keyboard. So this is the project on Thingiverse. This is the keyboard that we are building. So I need to look at the wiring diagram so that I get this right, because the left hand side works, but we're now working on the right hand side, so everything's mirrored. Gary, now we're not going to go there. I am going to be using some smooth on silicone and probably some smooth on resin to cast these. Yeah, this is true. Stating that you're off the beaten track assumes that you were on a track at the beginning, right? So yeah, I fully accept and own that point. You just got to own it, right? Okay, so let's have a look at the schematic and make sure that we wire this correctly. I so hope that I've done this right. Otherwise, I may have to revisit. I've just seen something on this schematic that makes me think I may have to open up the other one and fix it. But let's have a look first, right? Let's not prejudge. Right, where are we? Here's the schematic. I'm just opening up the schematic. Bring us onto this window, and then we can jump on here. Right, so this is the schematic. So this is the Pro Micro. Rubbish. So I just realized. Let me just confirm something here. I think there is something in this project which is a little off. So I went into the build log, right? There's a build log as part of this project. And in the build log, we've got a diagram. And the way that this guy has got this wired, let's open the image in a new tab, and then we can zoom in on it. Okay, so this is the underside of the Pro Micro, and you can see that PD3, PD2 it comes over here. Whoa, and forms the data clock of the I2C bus. Over here, we've got ground and VCC, right? Now, I've wired it like this. I have definitely wired it like this. However, when we look at the schematic... Okay, so first and foremost, these two pins on the board are effectively the TX and RX of the microcontroller. But when we look at the schematic, the TX and RX pins are not used for that purpose. We got PD1 and PD0 for serial data, serial clock. So I have an error in my wiring of the left-hand side. So we 100% need to fix that. If I plugged this in, we wouldn't release the magic smoke. It just wouldn't work. So that's somewhat of a relief, right? Let me just check here what the naming convention of this is. PD1, PD0. Okay, so I believe I'm going to have to do some research on the pinout for wiring this, which I'm not going to cover tonight because I ideally want to keep progress moving along. So we'll go back to the rows and columns wiring because this works, right? This does work on my Pro Micro for the left. So I know that the key, that the wiring is correct. So we are wiring rows. So row 0 goes to PD4. And bearing in mind, this is the underside of the board. So what is on the right is actually on the left. If that's not confusing enough for you. So let's get my iron back up to temperature. It's gone to sleep. And we'll start training our wires to reach. So what I'm doing, you'll notice that I've got this laid out like a book. And there's a guy on YouTube. He's been around for forever, right? Ben Heck. He's done a lot of like controller mods. He's turned Xboxes into laptops. He's done some really hardcore engineering with electronics. And one of the things that I learned from him was when you're wiring up your projects, you have them like a book, so that when you go to close them, they have a natural fold position. Whereas if you just kind of like wire it in a bit, you're trying to cram it in your project box and it doesn't fit, or something goes a bit sideways, right? So we're going to wire this like it has got like it's a book. So I'm actually going to super glue this in place, even though we're discarding this. We're going to super glue this into place so it acts as a jig for us to solder everything in place and have the wires cut. And all we got to do then later is to swap out the base. Okay, so a little bit of super glue. Where's my activator? Where's my activator? It's up here. It is up here. There it is, right in front of me. Come on, Steve. Wakey, wakey. All right, so just spray a little bit of activator on the back of the component that we're about to glue into place. Now line it up